Close your eyes for a moment. Breathe. Now, think of time. This very second that has just passed, where has it gone? The moment you're in right now, how long does it truly last? Centuries have passed while scientists sought to answer what appears to be one of the most simple, yet perhaps most mysterious questions in the universe. What is real time? Time, it flows, it moves, it carries us forward like a never-ending river. We measure it in seconds, minutes, hours. But behind those ticking numbers lies something much deeper, a concept that science still struggles to completely define. Neither in physics, nor in cosmology, nor in quantum theory, time is not a thing. It bends. It stretches. It might even disappear altogether, depending on where you look. Tonight, we are going on a journey across science and thought about what real time actually means in our universe. From the smooth rhythm of classical clocks to the tangled loops of spacetime itself. From human perception to quantum uncertainty. This is not just a question about physics, it's about reality itself. But here's the thing. Every scientific field talks about time, yet none define it the same way. To a biologist, time may be the rhythm of life, cells dividing, hearts beating, seasons cycling. Time, to the astronomer, is the slow pulse of the cosmos, the light from distant galaxies taking billions of years to reach us. To a quantum physicist, time can flicker, distort, or vanish inside a tangle of probabilities. But beneath all of this, there's a deeper question. If each branch of science sees time differently, what is the actual time that connects it all, then? Can such a thing even exist? Before Einstein. Before Newton. Before even the ticking of mechanical clocks, time was something humans felt. The rising sun. The length of shadows. The phases of the moon. These rhythms defined existence long before we named them ours. But then, in the 17th century, Isaac Newton gave time a new identity. He saw it as something absolute, steady, universal, ticking the same everywhere. A cosmic metronome, whose beat never varied in tempo. Time played the role of the stage on which everything else happened in Newton's universe. It didn't care what happened within it, it just flowed, eternal and indifferent. This view worked beautifully, for a while. It made sense for falling apples, for orbiting planets. But centuries later, the steady beat began to crack. In 1905, a young patent clerk named Albert Einstein looked at time and saw something astonishing. He proposed that time was not absolute at all, but relative. Now consider two people, one stationary, the other traveling at close to the speed of light. To each, time would pass differently. Seconds would either stretch or shrink depending upon their motion. This wasn't philosophy, it was physics. And that meant the faster you move, the slower the time flows for you. Later, Einstein's general relativity took it even further. It demonstrated that time is interwoven with space itself to form a single entity, spacetime. And spacetime bends in the presence of mass. In other words, gravity doesn't just pull, it warps time. On Earth, near the surface, your clock ticks slightly slower than it does in orbit. On the edge of a black hole, time comes to a near standstill. Einstein's equations showed one amazing thing: time is relative. It's local. It's elastic. And it depends on where, and how, you exist in the universe. If you could hover near a black hole for an hour, while your friend watched from a safe distance, you'd return to find that decades, maybe centuries, had passed for them. While, for them, time continued passing. In yours, it almost stopped. This isn't science fiction, it's proven physics. Satellites circling around Earth must adjust their onboard clocks because time passes slightly more quickly for them relative to us on the ground. Without these corrections, GPS would fail within minutes. So, whose time is real? Einstein's response was subtle. They're all real, just relative to their own frame of reference. But this creates a deeper mystery. If every observer possesses his own variant of time, What, then, is the proper, universal time of the universe itself? Does it even exist? Here's where things get even stranger. That is, in quantum mechanics, the physics of the really small, time starts to behave differently. Quantum theory equations allow for particles to be in multiple states simultaneously. They can be both here and there, both alive and dead, in the famous Schrödinger's cat thought experiment. But when scientists write down the quantum equations describing how these particles evolve, something curious happens. Time isn't always part of the equation. In the Wheeler-DeWitt equation, which is central for quantum gravity, there is no explicit time variable whatsoever. At its very deepest level, the universe may not tick. It might just be. Physicist Carlo Rovelli calls this the timeless view of reality. Indeed, he says that time is not fundamental, but rather an emergent property. A result of the way changes occur relative to each other. In other words, time may not be present until an event occurs. That's hard to wrap your head around because our brains are wired to feel time flow. But in the quantum world, that flow might be an illusion. Close your eyes again. Allow the seconds to move within your consciousness. That sense of flow, of before and after, is built into you. Your brain creates time. Neuroscientists have found that time is perceived as depending on neural oscillations, tiny rhythmic patterns in the brain. When you focus, time feels fast. It slows down when you are relaxed. In the mind, there is not a perfect clock but perception. Time can stretch or collapse in dreams. In the moments of danger, it freezes. In meditation, it almost disappears. So, physics says time can slow or vanish, and the brain says time can stretch or distort. Maybe real time is neither in the stars nor in our minds alone but in the mysterious connection between the two. One thing, however, seems not to change: time always moves forward. Eggs break but never unbreak. Smoke spreads but never unspreads. Memories only go one way, into the past, never the future. Physicists call this the arrow of time, the direction in which entropy, or disorder, increases. The universe began in a state of extraordinary order, the Big Bang. Since then, things have only spiraled towards chaos. This gradient, in which order yields to disorder, provides time with its directionality. But why? In the first place, why did the universe start off in such an ordered manner? Nobody knows. Some scientists believe that time's arrow emerges from quantum entanglement, which is a way particles connect, influencing each other's histories. Others think that it's connected to the expansion of the universe itself. Either way, the arrow points forward, and carries us all with it. Now, imagine zooming way out, beyond planets, beyond galaxies, to the structure of the cosmos itself. In cosmology, time is measured by the expansion of space. The universe, following the Big Bang, has been expanding for roughly 13.8 billion years. That number, 13.8 billion, is our cosmic time. But that measurement, too, is dependent on where and how you make the observation. Cosmic time may run differently in areas where extreme gravity occurs, such as around black holes. In the distant future, if dark energy continues accelerating the universe's expansion, then galaxies will drift apart to a distance so great that their light cannot reach each other. To those far-off observers, time would seem to stand still, as if the universe itself had grown quiet. Now, modern physicists look for a unification, the single framework that combines quantum mechanics and relativity. It's called quantum gravity. But one of the biggest challenges in building it is time. Time, according to general relativity, is smooth and continuous. In quantum theory, everything is discrete, made of tiny, indivisible packets. How would you combine a smooth flow with a granular one? How can time be both continuous and quantum? Some theories suggest that time is an emergent property of entanglement, how information knits the universe together. Some say time might be made up of loops of energy, so-called spin networks, that constantly shift their shape and give rise to what we experience as time. But in the deepest equations, there may be no t at all. Just relations among events, patterns describing how things change without reference to an external clock. So the real time in science might not be a river flowing forward, but a vast network of relationships, persistently updated, both timeless and ever-changing. Here's a thought that bends the mind. What if consciousness itself creates time? Roger Penrose was one of the great mathematical physicists who once expressed a hypothesis that consciousness and quantum processes are intertwined. That somehow, awareness can emerge from the collapse of quantum states in the brain. If so, then perhaps the flow of time we feel, the sense of now, is a byproduct of that process. Maybe time isn't just something we live within. Maybe it's something that we generate. That concept blurs the boundary between physics and philosophy. But it is not without support. Recent experiments on quantum entanglement have demonstrated that the order of events can, in fact, sometimes be uncertain. One thing can happen before another, or after, depending on how it's observed. So what if there isn't a single timeline of the universe? What if reality were a tapestry of overlapping moments, and our minds weave them into the illusion of a smooth flow? Today, physicists are constructing the most accurate clocks ever made. With optical lattice clocks, it's possible to measure time with an accuracy that would only lose 1 second in the age of the universe. These instruments don't just tell time, they define it. They serve to test fundamental laws of physics, measure the stability of gravity, and even search for changes in the constants of nature. Soon, quantum clocks could help us map spacetime itself, showing how time changes from place to place with breathtaking precision. And yet, even as we build these perfect clocks, we are still haunted by the question that has followed us for centuries. Is time something that exists outside of us, or something which exists because of us? Let's take a step back. If Einstein showed that time bends, and quantum theory suggests that time may disappear altogether, and neuroscience reveals that time is perception, then perhaps the universe's real time isn't a clock at all. Maybe it's a relationship, a rhythm of change connecting everything. Think of the universe as a grand symphony. Every particle, every star, every thought playing its note. Together they make harmony. And what we call time, it's just the music of that ever-changing song. A melody without a beginning or an end. Only transformation. So, what is real time in science today? It's not the seconds ticking on your watch. It's not even the flow you feel in your mind. It is a concept that stretches from the smallest quantum events to the largest cosmic structures. A bridge between existence and perception. Time is the language the universe uses to tell its story. And that story is still unfolding. Every discovery, every new equation, every photon captured, every heartbeat measured, brings us one step closer to the truth. But the beauty may be in the mystery itself. That something as ordinary as a second might hold the key for everything. If this journey through the nature of time sparked your curiosity, tell me, what do you think time really is? An illusion? A dimension? A feeling? A rhythm of change? Leave your thoughts below, and let's explore this mystery together. And should you want to keep diving deeper into the wonders of science, check out my next video, where we explore how the universe itself may be conscious. Until then, take a breath, slow down, and remember, every second is a miracle.